The vanishing reason your groundwater hoards river water from you, and in the Rio Grande Basin 2022, it swallowed 36 miles of continuous flow without a single raindrop's help. That water didn't evaporate. It didn't run to the sea. It went down, into the same ancient system that fills your tap, and the mechanism that pulled it under has been running beneath your feet your entire life. You've just never felt the suction. Right now, beneath every road you drive, beneath every field that grows your food, beneath cities holding millions of people, there is a slow-motion heist underway. It has been happening for a century. It accelerated the moment we started drilling wells at scale, and in the last decade, it crossed a threshold that groundwater scientists don't say plainly in press releases. Aquifers, the layered rock formations holding the majority of accessible freshwater on this planet, are not just sitting there storing water. They are consuming it, pulling it, generating suction through limestone and gravel and fractured sandstone that reaches all the way to the surface. And rivers, which you probably assume flow from snow to sea by gravity alone, are losing that race right now. Here's what they don't teach in school, and what changes everything you thought you knew about rivers. Most rivers are not just outflows, they're inflows. Groundwater seeps upward through riverbeds, rising from pressure below, keeping rivers alive between rainstorms. Hydrologists call these gaining streams. They gain from the ground. And for thousands of years, most rivers in inhabited zones were gaining. The earth was pushing water up. The system was in surplus. That direction has reversed. Across the American Southwest, across Spain, Morocco, northern China, rivers that flowed for millennia have begun bleeding water downward. The aquifer beneath them has been pumped into such deficit that it no longer pushes. It pulls. Riverbeds have become drains. Water that should move toward the sea is instead moving toward the same taps, the same wells, the same municipal systems that helped empty the aquifer to begin with. The Rio Grande lost 36 miles of continuous surface flow in 2022. Not to a heat wave, not to a dam, to suction. The ground was thirstier than the sky. You might think this is a water rights problem, a farming problem, something that happens in places you'll never go. Here's the pattern interrupt. Conservation doesn't fix this. Cutting your shower by 2 minutes doesn't fix this. Efficient irrigation doesn't fix it fast enough, because the deficit is now structural. The empty space in the aquifer is the mechanism. The hole is what's doing the pulling, and you cannot outconserve a hole that took 100 years to dig. What that means, and this is the part that stops researchers mid-sentence, is that surface rivers and underground aquifers have crossed from two separate systems into one feedback loop, and the loop is running in reverse. This is where it gets strange. This is the deep part. Scientists monitoring the Santa Cruz River in Arizona watched something they had no existing framework for. A river that had been dry for decades began flowing again, not after a flood, not after unusual rainfall. It returned slowly in sections in open desert. They called it perennial flow, water returning to life. When they traced the source, it wasn't snowmelt or storm runoff. It was treated municipal wastewater, water the city of Tucson had been releasing for years, slowly percolating into the depleted aquifer and then being pushed back to the surface. The aquifer was so empty it had developed a reverse pressure differential, a vacuum where groundwater used to be. It was drawing treated wastewater upward through sediment and returning it to the surface as river flow. That's the callback. The river didn't just lose water. It became a receiving dish for whatever went down first. In Phoenix, in Los Angeles, in Karachi and Madrid, groundwater models now show aquifer depletion accelerating at the exact rate surface water flow is declining. These aren't parallel crises. They are one mechanism. A single planetary pressure system running a deficit with no natural recovery timeline under current extraction rates. The ground beneath you is not a reservoir, it is a pressure system. And it is losing pressure faster than rainfall can restore it. What that means for your tap specifically is this. The water you drank this morning may have fallen as rain 100 years ago. It traveled through rock formations for decades before reaching a well. Along the way, it passed through aquifer zones fractured by overextraction, rock that cracked as water was pulled out faster than pressure could equalize. As those fractures spread, filtration slows. Water that once moved through dense, fine-grained sediment, the kind that strips contaminants over decades of slow transit, now moves fast through open rock. The natural filter is breaking. You don't know which path your water took. Nobody does. The tracing technology exists. The mapping doesn't. So here is the question that hydrogeologists haven't answered and that no one is racing to announce publicly. If a depleted aquifer can reverse a river's direction, pulling surface water down into the dark, what happens in coastal cities where the aquifer borders the sea? In Miami, in Jakarta, In Mumbai, saltwater intrusion into coastal aquifers is accelerating. The official explanation is sea level rise, but the rates don't match the models. Something else is pulling it in. The empty space beneath is generating suction, and the ocean is beginning to answer.